Good afternoon and welcome to the fourth webinar from the UK Atomic Energy Authority on the challenges for fusion. My name is Ian Snell. I'm the Fusion Skills Outreach Manager for the Foster Programme, helping to organise this series of webinars. Today, our main presenter is Jakub Jodlowski. He's a Senior Engineer from our Materials Research Facility. He'll be presenting a presentation on enabling material research and technical capabilities. I also have with us Imogen Hayden, who is a second-year graduate in the Materials Division. She's also been an information officer on the graduate committee, so she'll be telling us a little bit about her experience on our graduate scheme. As per previous webinars, we'll have about a 30-minute initial presentation from Jakub. I'll then hand over to Imogen for 5 or 10 minutes about our graduate scheme, on other opportunities and her experiences. Then we will take questions and answers. Well, I will pose any questions that you put into the Q&A tab within Teams to our presenters for as much time as that takes. We should be aiming for a total time of about 45 minutes, possibly a little bit longer, depending on how many questions you have. So without any further ado, I will pass over to Jakub. Thank you very much.
Thank you. Hello, everyone. It's great to meet you all. So welcome to my presentation on enabling materials research and technical capabilities. I have half an hour and 40 slides, so I'll have to rush through it. If there is something that you'll be keen on knowing more, please contact our comms team or anyone who will kind of help you with pointing you out to either one of us, so we can clarify or extend some of the stuff that will be presented here. So UKAEA, why we are all here. So if you know, there is a growing climate change, and we are burning more and more fossil fuels. There are so many natural disasters and economic damage and so on and so forth. So we are trying to help and prevent that by working on fusion. As that, I will give you a short recap on what is nuclear fusion. So this is an introduction to my materials presentation. So the most known fusion reactor is our sun. So this is the one that we always are trying to capture whenever we are saying what is our organization doing. It is trying to build a star on Earth. So basically the sun, sorry. In order to understand fusion, we have to look into the atom structure. So fusion is basically combining two smaller atoms, so they fuse together into a bigger element, and this is essentially how the fusion more or less works in a very simplified way. So please don't quote me on that. But with this being said, you might know that there are 3 or 4 states of matter, and there is solids, liquids, and gases, and superheated gases will create plasma. So this is something that we need to our fusion reaction. So once I've said that, in order to get that plasma, we have to have certain parameters in our reactor. So first of all, we need a fuel. So we are using hydrogen. We need high temperature, so it is at around 15 million degrees. We need high density and high pressure. All of that combined together and captured in the reactor, let's say, will help us with delivering fusion. And why we are actually doing it is what you can see here on the right hand side. So we are trying to take out the current energy sources that are like fossil fuels and change them into fusion. So we've got the base load that we are working that will essentially replace coal and oil and anything that is the fossil fuel. And this is our area where we can actually strive in the future, and where we can actually deliver the biggest impact. With that being said, we are located in column, so it is just around Oxfordshire, and we've got a beautiful column site that you can see here. UKAEA in general, as you might already know, has several there are several parts to it. So there is JET, so the Joint European Torus that is currently in the commissioning. There is MASS, so it is another reactor. Then there is RACE, so robotics and remote handling. There is the MRF, and there is OAS, so our training facilities. Today, and STEP, sorry, I've missed the important one as well. So today we'll be discussing the Materials Research Facility, and this is where I wanted to take you through our little tour. So in order to deliver fusion on Earth, what we are doing is we are trying to collide tritium and deuterium, which, as you know already, will fuse and it will create helium. But as a part of this reaction, we will have an extra neutron. So this is the stuff that we're trying to capture. And in order to do it, we need a device. So the device is called tokamak. This is an abbreviation from a word in Russian, I think. And we are trying to confine plasma. So what you can see here in a pink donut shape inside, we're trying to confine it with massive magnets. So we've got these toroidal coils, we've got poloidal coils, sorry, and we've got the central solenoid transformer that works as a spark. So I was thinking that if there will be anything that I wanted you to remember from this presentation, actually there are two things. One is now and one is at the very end. Is that my favorite comparison of the tokamak is to just massive donuts with some magnets around it. So this is more or less the technology that we are trying to do. Very simplified. I hope that our comms team will not tell me off about that. So key materials challenges. So you will see that we need to understand the high temperature creep. We need to understand what is happening with materials, either cryogenic temperatures, they are losing ductility, there is a transition from ductile to brittle, there is neutron radiation, so there is radiation hardening, and there are challenges that are involved with that. There are coolant materials and interaction with that, corrosion, etc., etc., etc. Then we've got high magnetic fields. So this is something that we are focusing a lot right now. So superconducting magnets and large forces and stresses on these components, and tritium. So understanding the permeation barrier and locking up the valuable fuel. As I said, and this is, let's say, the outcome of the materials challenges, but I wanted to give you a picture against the words. So where we are trying to find these things. So this is a tokamak. This is actually a picture of our jet reactor. So the example materials that we are testing is the first wall, is the blanket materials, is diverters, and a lot of supporting components for these. So it's actually quite interesting that for each of these materials, for blankets, for first walls, for diverters, there will be slightly different material compositions and so on and so forth. So we will test a very much of a range of composites, metals, and so on. So our UK Atomic Energy Authority's response to all this research, to all this need, is actually a materials research facility. So the facility that myself and Imogen is working. So the facility is laying down somewhere in between the UKNNL and universities. So if you are, for example, a university student and you will be working with radioactive materials, you will be working more or less with materials at around 150 megabecquerels of cobalt-60 equivalent. Then anything over that is something that we would be your kind of research facility when we are enabling materials that are having higher activity than this to be tested in our facility. Although we have also a limitation, which is 3.75 terabecquerel of cobalt-60 equivalent, and after that it is a high activity samples. With that being said, in our facility, we divide our facility in 4 main, let's say, testing areas. So we are working on sample preparation, on thermophysical characterization, microstructural analysis, and mechanical testing. So these are the 4 focus areas that we are working on. And these would be the pieces of equipment that we have available. So if you would also be interested in research and collaboration with us, you already know what you could potentially do in our facility. A little bit of an enabling work now. So I will give you a little bit of a history about the facility as well. So what we are doing here is we are taking our medium activities and we divide them into 4, let's say, process points. So there are samples that come up to our facility that are non-active. So then we handle them by hand. There are human handleable samples. So they are under 10 microsieverts an hour at 30 centimeters. But then also we've got samples that's at something that we call state 2 samples that are over 10 microsieverts an hour at 30 centimeters. And then these samples would be actually handled by our robotics systems. So we are taking human out of the picture. So we're trying to keep everyone safe and making sure that everyone goes home and doesn't get any radiation dose. And this is then happening with the usage of a robot. So I will have some pictures for you later. And we also take the highest activity samples in our facility, and then they would be worked on in a hot cell line. So this is something that I will show a picture of in a second. More or less, it looks like that we've got a set of glove boxes for the low activity samples, then a set of research rooms where in each one of the research rooms you will have a robot, and this is how we would test our samples. So I know that this is a lot of words, so I wanted for you to imagine that you are actually the scientist that has a sample and would like to take it through a tour or a testing activity in our facility. So I've got a typical journey of a sample through the materials research facility. So first, the sample would be received in a hot cell line where it would be weighted and measured. So we would try to understand what is the gamma signature on your sample, what actually is the material, and what is its weight, and if it matches what we were expecting from the sample to be. After that, we would clean your sample and polish it. We would post it out, and with our transfer trolley, which you will see in a second, we would move it to a shielded research room. And with that being said, let's start with explaining and seeing actually what these points 1 to 6 really mean. So first, this is our hot cell line. Actually, this picture is taken in, I think, 2016. So our hot cell line has 2 additional hot cells right now. But this is the picture that I like actually the most. So you can see that we've got on this picture, there is a line of 3 hot cells and a receipt cell. So in the receipt cell, this is where your sample would be unpackaged, and there is a robot inside that would do the unpackaging. So this is a slightly different view of the receipt cell. So you see here that we've got a transfer tunnel that with this transfer tunnel, you can actually access hot cell number 1, which I will show you in a second. Hot cell number 1, so our inspection cell is where we would have, when we would be inspecting your sample, we would have potentially we would have an optical microscope, we would have a gamma detector as well. So this is where we are trying to see if what you've sent us is actually matching the expectation. Then we've got a preparation cell where we've got a diamond cutting saw, we've got a polishing equipment. We've got and then we've got a transfer tray to the next cell, which is a post-out cell. What is very important, and you can see it here, that there is no human access to these cells. We are using a remote manipulator. So this is our CRL manipulator to handle the samples. So actually on the next picture, you can see that our operators would stand outside of the hot cell, and they would use either a lead glass window, either cameras to see through to the inside of the hot cells. There is a great picture of one of my colleagues that is actually working in the team with me that handles samples from the yeah, so the picture was taken inside through the window to see him outside of the cell. So this was done when the cells were in commissioning. So after your sample would be taken through the whole process. In hot cell number 3, we've got a posting port into which we slide a transfer. Oh, sorry, my mouse got stuck. A transfer trolley. So this is a 450 kilograms trolley that we post samples in and out the hot cell into the research room. So you can see here an operator that is transferring the trolley inside the research room. And on the next slide, I will show you our robotic systems and remote handling in the research room. All right, just to not lose time, I will maybe ask our comms team to share the video with you later on, but I would just explain what is happening. So on the video, you will see that is actually this one that I'm pointing right now, that takes a sample from the shielded trolley to our shielded castle, and then from the shielded castle to the equipment. In that case, this is a research room, I believe, with an SEM inside. So the sample will be moved from the shielded trolley to the castle, and then out to the SEM. So this is what our operators would see. So you see that this is a person that is working as a technician at our facility. But what actually you as a scientist would see is this. So this is a screen in our control room. So all our science is actually happening remotely. So people are not next to their samples, and they are not next to the radiation, essentially, because this is in a shielded room. In the same building, but in a different area. But what you would see is actually the scientific equipment and the science behind it. So this is a picture of our control room. So the little banana-shaped desk is representing every of the scientific set of scientific equipment that we have, and this picture represents one of the scientists that are working on that. With this being said, the science that's happening. I've got an example of one of the science that we are doing. So this is in situ identer done on focused ion beam. So you can see there should be a scale. Oh yeah, so it is 10 micrometers. The samples that we are testing. So you can see. I think that my favorite video is actually the third one and the fourth one. So this is a focused ion beam tip. So you can see the size of the cantilever that we are trying to bend. And here, just on the very end, you will see a crack at the end. So these foils is, if I remember correctly, they are 1/10 of a human hair size. So with irradiated materials, research on them. Generally, and especially in our facility, what is happening is that we're trying to have as small material as possible so we can irradiate. Sorry, if I will say it again, I think I will fail again, so I will just skip that. We're trying to have as active material as possible, so the material will be as small as possible so we can put as much activity in the material as possible. I hope that it makes sense. I'm really sorry if it doesn't. What we are trying to find is radiation damage. So actually, you can see that these are examples of our electron microscopy of atom probe tomography. You can see here clusters of damage and also some infusions of materials into a top layer. So this is pretty interesting, and these data then feeds into our teams that are trying to build a strategy for building the fusion reactor. With this being said, what are the users and customers that we are working on? So we've got around 70 I would say 60-40 split. We've got internal customers, so it is our materials division and the research that we are producing, and external organizations such as universities and research institutes. What is actually interesting here is that we also, this is my favorite part of this presentation, we are also doing forensics for example, decommissioning. So sometimes you might hear and see in the news that JET, the Joint European Torus, is currently being decommissioned, and it is a piece of history, machine built in the 60s. So you can imagine that there is a lot of knowns, but sometimes there are some unknowns, and we are actually trying to help the commissioning team to find what kind of materials they were using, what they have, what is the behavior post irradiation. So actually, this is my favorite part of our work. With this being said, what is the next steps in fusion power? So I've mentioned JET, but there is also ITER that we are strongly contributing into, and this is the International Tokamak experimental reactor. So this is in southern France, but also locally for us, we are contributing to building STEP. So this is the spherical tokamak that is designed and will be built in West Burton in the UK. With this being said, I think that because you are on several of these sessions, you will see that enabling fusion takes a lot of people, expertise, areas of expertise in order to deliver it. And we are just here. Material science is a very important one of the I would say 6 pillars of the fusion. So it is pretty interesting to see how our work impacts the graded fusion research. But I would ask you something actually. Is it worth it? If you would have to kind of think for the next 3 seconds, is it generally worth to deliver a project that will benefit the humankind, that will realistically save all the energy crisis and every, or like maybe not every, but a lot of problems that we are having? So think about it like that. This is actually the data that I verified yesterday. So cost of ITER currently it's 26 billion pounds. I think that maybe I've made a mistake and it is dollars, but I think I will have to double check that. But it's around that value. Sending people to Mars, it's around 80 to 100 billion dollars. But now Qatar World Cup is 200 plus billion pounds. Sorry. So you can imagine that that our work and our contribution is somewhere here, and we are trying to deliver something that will be a game changer to the humanity. You know, meanwhile, humanity chooses that. So with that being said, I've got a summary slide which says materials research is important because at the end of the day, everything is made out of atoms. So everything that surrounds us is made of atoms, even us. So it is pretty interesting to be in the materials research. With this being said, that is the end of my presentation. Thank you very much. I hope that it was not rushed too much. And if you would have any questions, feel free to reach out to our comms team.
Great, thank you very much, Jakub. I can see there's already a couple of questions coming in. I'll approach those later, but I'm going to hand over to Imogen to just give us a brief update on the graduate scheme and her experiences.
I will just attempt to share my own slides, which will not be used extensively, but mostly used as starter people. There we go. So I'll use this slide as a background while I do a little introduction. So yeah, as Ian said, I'm Imogen. I'm a graduate material scientist here at UKAEA. I'm on my 2nd year of the graduate scheme now. So I joined back in 2024. Yeah, can't get my maths right. And I actually also started, so before I was a graduate here, the summer before I did a summer placement during my degree as well. So leads quite nicely onto the summer placement scheme. So the summer placement scheme, we have a few different schemes that we can do. student placement schemes. We have the summer placements, such as what I did. So I spent 11 weeks here working in research, and actually the project that I was doing my placement with is a project that I still work with now. So that was quite nice to kind of carry over. But we also do industrial placements for people who do kind of a year in industry type thing. And as well as kind of the placements that we do directly through ourselves, there are other placements that are offered through other kind of routes, and also the Foster summer internships, which are funded by us through the Foster scheme, but you are placed directly in a university or another organisation. And one thing that I will highlight on this slide is the placements are a fantastic pipeline for students to join UKAEA, either through the graduate scheme or as a direct entry. So I obviously did that and joined into the graduate scheme. And actually, with my year, we had a scheme that was called advanced application. So by doing the summer placement, I did an advanced application to the graduate scheme. And so I didn't get my pick of graduate scheme roles, but my graduate scheme role was allocated before the public got the adverts for the roles, which was quite nice to know by Christmas of my final year that I had a job lined up when I finished. And onto the actual graduate scheme. So our graduate scheme is a 2-year development program. We join in a permanent role. You may well have heard a lot of this before. One thing I will say is that in my experience, the 20% development time that we have is actually a fantastic opportunity. So as Ian mentioned, I do spend some of my time working with the graduate committee. So that's a committee of graduates who organize part of the graduates and we kind of provide other opportunities. So my role in particular, the role I currently have, is a lot about kind of information and communications. So I kind of digest all of the information things that we have coming into us and give the more relevant ones to the graduates in various different ways. But some of the other things that I kind of do using my graduate time is I've done training courses. I've just in the process of finishing up my graduate project, which is where you spend a few months doing a project with kind of in another part of the business. So I've been working with kind of the commercial and the procurement team for a few months, learning about what they do. And actually on Tuesday, I have to present a poster about what our group have learned in that, which will be really good. And another thing that I've spent time doing is working with the disability network that we have here. We have various staff networks, and I do work with the disability network, mostly as both outreach externally and in-reach within the company, and generally kind of helping the committee with some extra time. But I would say that the graduate scheme is a really fantastic place to kind of develop your career and also develop as a professional person. It's kind of very wide-ranging in the things that we do and kind of all of these different things that come together. So it's not just in your role. So for example, I've changed my role a few times kind of as I've gone through the scheme, but I've definitely developed as a material scientist as I've gone through, and I'm much more competent in a lot more things. And so that's kind of both the kind of professional development there and my kind of scientific development, as well as the development as an employee and as a person. So yeah, I think this is some examples of the kind of things that were vacant, the vacancies that we had for this year. They are, I think, all filled now, but you can have a nosy on the UKAEA website if they're not. I'm down there at the bottom middle as a material scientist is where I work. But as you can see, we have a wide range of things that are available kind of in science, in engineering, in IT, be that more software, be that more kind of computing. But we also have people who do kind of the project management, the supporting functions is what we call them internally, but the procurement, kind of the finance side. We have graduates across all of those as well. And then it should also be mentioned that we do postgraduate opportunities. So I think Foster in particular is helping fund some master's projects. I'm not sure on the complete details. I'll have to ask Ian on those. But also as UKAEA as an organisation, we kind of support and part fund some PhDs, particularly if you look at the fusion power CDT and the fusion engineering CDT. A lot of those have kind of a UKAEA involvement, unsurprisingly as they are fusion. But outside of that, we do also fund kind of particular PhD projects at various universities as well. So yes, I think early careers at the UKAEA, their website that they have is very good to kind of look at and be able to see all of the opportunities. So if you weren't listening or I didn't explain it well on this, it's on a lot of things are on that website, and they also share the vacancies that are available when they are.